Thank you very much for the invitation, I'd like to say. This is work that I've done with a number of collaborators, including Deborah Solsky and Howard Schreier from UNM, Elizabeth Hunke from Los Alamos, and Pavel Bochev and Biljana Paskelova at Sandia. So I'm going to, I guess, start from the big picture and look at some motivation. Why are we really interested in modeling ice for climate? And the main thing is that sea ice plays an important role in regulating global climate. Right? It reflects solar radiation, it insulates the ocean from the atmosphere, and it can influence ocean circulation and wave action as well. We know that the Arctic is changing rapidly due to feedback effects. I show, let's see if the, all right. So in the plot down at the bottom is summer ice concentration going from 1970 to 2017. You can see there's a sharp loss in ice concentration, somewhat less of a sharp loss in the winter, but still a decrease. And we also have, there are a number of works that have looked at ice volume as well, and we know we're losing ice volume. Here, this is a plot from Kwok and Rothrock, where they look at submarine data, the dark blue lines from the 50s and through the 70s, and then red or later sub from the 1990s, and then the light blue are the ISAT records. And so there's a significant decrease in the ice volume as well. And I would really argue that dynamics have an important effect on the mass balance of ice in the Arctic. So it's not only just as the ice becomes thinner and weaker, you're going to have more export of ice, but also when you have the dynamics and the growing of leads, where a lot of the ice production happens in the winter, is very important for creating new ice. So I just want to stress again the importance of leads and cracks in the ice. So in winter, the heat transfer between the ocean and the atmosphere occurs primarily in leads. Again, as I mentioned, it's where new ice production happens. And we see a lot of deformation in the ice. And so we've seen lots of these pictures. I'm going to show a lot of RGPS, just like everybody else has. And you can see these large linear features that are associated with leads or complexes of leads that are important in the Arctic. And so in terms of this large-scale modeling, there are a lot of processes that have to be included. And so one of the big things, of course, is getting the annual cycle of growth and melt due to radiative forcing correct. So on the left there is a picture from NASA for a typical summer extent of the ice and then a typical winter extent. So you see there's a large variation that has to be taken into account. Then we also need to understand the mechanical deformation due to the surface winds and the ocean currents. And then we want to include variations in thickness. We want to be able to handle leads and ridges in the ice. So that leads to the governing equations. We've also seen some of these before in the presentations, but I'll go over just a little bit more just to summarize. So we solve a 2D momentum equation for ice velocity in these climate models, and this is essentially, you can think of this as a shallow ice approximation. You integrate through the thickness to get this, and so we have, instead of a density here, we have mass per unit area, and our internal force uses a depth integrated stress tensor, that's N, and we have forcing from atmosphere, ocean, Coriolis, and sea surface tilt. So the conservation of mass and in these equations is usually handled through an ice thickness distribution. Many sea ice models use an ice thickness distribution. So what essentially you're doing is carrying around in each grid cell a probability distribution of thicknesses for the ice. And that includes open water. There's a fraction of open water and a fraction of thicknesses of different bins when you discretize. And so you solve an advection equation for this thickness distribution. And so you have a horizontal advection term and then an advection in thickness space. And ridging comes in here. The ridging functions can be fairly complex. You want to ensure that you conserve volume, but then redistribute based on converging flows. And then finally, for each thickness category in each cell, you would solve a 1D heat equation for temperature, and then which will give you changes in thickness, average thickness for that bin. So the stuff I'm going to be talking about is the rheology. So it's one small piece in this larger model for sea ice in the Arctic or Antarctic. And as we mentioned last night during the discussion, there are a lot of things that affect how well we can predict sea ice, and rheology is only one small part. But I'd like to be a little more optimistic than maybe some are, even though in coupled climate models, ocean and atmospheric forcing are very variable and they can have a strong impact on how the ice behaves. I still think it's important to get the ice model as right as possible so that if we use known forcing, we can get what we expect. And so there is value in bringing in new good models that rely on some of these more detailed fracture information and other things. So in terms of the standard sea ice rheology, this has been mentioned in previous talks as well. Generally, it's variations on the viscous plastic rheology shown here. Epsilon is the strain. We have bulk and shear viscosities with an elliptical yield curve. And then the yield curve depends on this ice strength parameter. There are other functional forms for ice strength that are used, but this is the original one, and it depends on only concentration and thickness. So all of the weakening occurs isotropically in this type of a model. There's a variation on this that's used in, for example, the Los Alamos CICE code, which is an elastic viscous plastic rheology. And in this case, it's not really a physical elasticity. The elasticity is used just to regularize this. So in the standard viscous plastic, if you go to very small strain rates, right, the model will blow up. So there are different ways to handle it. If you add this elastic term, you end up going to elasticity in the limit of very small strain, and it just makes the model better behave numerically when you're solving. So one of the drawbacks of the viscous plastic rheology is it assumes isotropic strength. So the strength only depends on thickness and concentration, as I mentioned. It was really developed when grid resolutions were on the order of 100 kilometers, and so you could make the argument that there were a lot of systems of cracks within that grid cell size so that the weakening could be considered isotropic. But as we go to higher and higher resolutions, so even climate models today, they're reaching to try and get to 6 to 10 kilometers for the ice component. And at that scale, it's certainly true that a single crack can dominate the deformation. And you can also see from the RGPS as well that you have these large linear features that go on for quite a distance. So I was actually going to show the same video that Veronique showed. It's quite a striking thing. So these are some still images from that same event. So it happened that year that in the Beaufort, the ice cover was actually pretty thin. It was mostly first-year ice, and there were a series of very strong storm systems that went through. And so it was a very striking fracture event that happened there. And you can see, I just want to point out the scales here, because I'm sure you can't see them where you are, but this line is 200 kilometers. And here, we're going to blow up this region down here, and now we're at 20 kilometers. But if just consider that how huge that fracture is at those scales. And so it's certainly true that you wouldn't expect the response to be isotropic in that case when you're looking at how the ice will move due to internal forces. So there's been a lot of work on developing anisotropic rheologies. And this is not even a comprehensive list. We saw a very nice talk just before this on another type of rheology. And I'd just like to add, just to throw in there, that there may be a point, given the expansion of the marginal ice zone and the melting and the loss and the deconsolidation even of the pack ice, where maybe we need to look away from continuum models for sea ice. And so there has been also work on discrete element method models. And I just want to put a quick little plug in. There's a newly started project that I'm working on. It's led by Adrian Turner in Los Alamos, where we're looking to create a discrete element model for climate modeling. So if everything goes well and we can get it to work numerically and be fast enough, it would potentially be a model that could replace, for example, MPAS sea ice, for those of you who are familiar, in the Acme code. And so these two pictures, I just want to point out again, it's from the same big cracking event. And you see, you do see some large continuous cracks, but then at later times you really do have so much breakup that it looks somewhat granular. So I was really intrigued by the last talk where it's trying to go from a continuum to a granular type model, and in fact maybe that is the proper direction to go in the future for sea ice models. But I'm just going to focus in my talk on one single anisotropic rheology, and it's due to Schreier. And that's the elastic-decohesive rheology. And what we do with this is we assume that leads are displacement discontinuities. We model the intact ice as elastic, and we can predict initiation and the orientation of the leads. And then once failure begins, the model is anisotropic. So our yield function looks like this. It's a little complicated, so I'll kind of walk through the different pieces of this. We have a brittle component, which is up here in the exponential. And we have, this is a shear component. So here we have a tangential traction and a shear strength for the shear term, normal traction, and tensile strength. And then we have the sigma TT component and a compressive strength. And this is to incorporate the effects of compressive. We want to incorporate compressive failure in this, including things like axial splitting. And then F here is a softening function. So it starts at 1 and goes down to 0. So UN is the normal opening I'm going to probably call it a crack throughout, but I just want to specify that these we can't really consider these as single cracks. Again, we're looking at very large scales. U0 as a parameter that defines at one point the crack is completely open. So since it's a cohesive model, you don't lose strength right away. You lose strength over time once you reach U0. And so for the scales we're looking at for the large calculations, we're thinking of the U0 of 500 meters or something. So these are not small crack widths. And in terms of the yield curve, so here we have yield curve in stress space. So this is phi equals 0 is the line here. And the arrows on here indicate, the blue arrows indicate the principal direction of stress, and the red indicate the normal direction to the failure surface given that principal direction. And so the idea behind this model is we really want to transition from brittle failure into ductile failure. And I just want to say that that Buck Schreier, who is the main developer of this model, really was really motivated due to the data from Erlen to try and get to capture all these types of cracking effectively with the model. So again, brittle tensile, also brittle tensile, and then axial splitting, and a ductile failure. So in terms of the rheology, we're assuming, as I said, strong discontinuities. So our displacement field has a smooth component and then a jump. This is the heaviside function along the crack distance. Then our strain, we have a smooth component of the strain and then a discontinuous component of the strain. And for a constitutive relation, we have E is our elasticity tensor, and here the epsilon is the total strain, and this is the decohesive strain. So elasticity for the smooth part, this is the smooth part here, and then we're using, in order to get the evolution of the jump in displacement, we're using an associated flow rule. In practice, we have to regularize that discontinuity in some way. So we're using a smeared crack type of approach where we have a length scale that's associated with our grid size to regularize. In terms of how we solve this type, it's a little more complicated than the viscous plastic model where you can solve directly for the stresses. But the algorithm is very much like an elastic plastic model, for those of you who are familiar. So we compute a strain increment from the velocity and then compute a trial stress from that strain increment. We take the maximum of the failure function, which will tell us what the failure direction is. And then we can evaluate the failure function for that normal n. And if we're inside the failure function, we're in the elastic regime, but if not, we use Newton's method to find the decohesive strain such that we land back onto the failure function. And just here's for a simple example of a tensile type failure. So here's our yield function. If we imagine we have a path along this dotted line, we hit the failure surface, and we initiate failure in the same direction as the maximum principal stress, or with a normal in the direction of maximum principal stress. Now, since we don't let the strength go to 0 automatically, we evolve. The failure surface will essentially pulls in. We reach a point where we hit that value U0 for the opening, and then we open completely and have a free surface and no more strength and tension at that point. So when you're doing for short-term simulations, it's probably okay to use that as is, but if you want to use this type of a model for any longer-term simulations, you need to have a way to heal cracks again, because of course ice will come back together and refreeze. And so we have a very simple way of handling that. We modify the softening function. If you remember, that is the linear function that takes you from initial damage down to fully open or fully no strength. So we keep the same function if the lead is opening or closing, but if it's closed and UN is less than or equal to U0, we allow freezing to start. So after some amount of time, we allow this function to increase, and then we cut it off actually at 1, because we're not going to make it stronger than the original. 1 will make it back to the original strength of the material. And we haven't done a lot of studies on this, but there's probably good data we can compare to get better times for this. You can think of the change in this function to be related to the ocean and air temperature and some reference temperature. But it's a simple enough algorithm that you could fit well to any data you might have. So we've seen a lot of RGPS data already. I'm going to show some more. Just want to go over basically what it is. It was developed by the Polar Remote Sensing Group at JPL, and it's a way of extracting ice motion data from SAR imagery. So it puts down a grid at the beginning of the season and then follows that using area and feature-based tracking. And you can get measures of deformation, divergent, shear, vorticity derived from the displacement. For our model, we want to compare to the cracks or the aggregate cracks that we're predicting with our model. And so we wanted a way to pull out information on discontinuities from the RGPS data. And we also actually will need this for initialization of certain models. So we developed a way to predict cracks in the RGPS data. So here's a simple, small region. I hope you can see the white grid. It's a little bit faint along here. Given the previous time and this time, you can extract deformation measures from this. You can get a strain. And given your strain, we're going to assume that all the deformation is due to a discontinuity. So our strain is going to be of this form. And then you can actually use an SVD to pull out what the components of the jump and what the components of the normal are for this. And so if we do that, we get a picture sort of like shown here. If we do it for all grid cells, it's going to put a crack in all grid cells, but of course that's not necessarily what we want. So if we put a limit on the size, then we get sort of what we would expect, where we have large cracks, then we're pulling out of the RGPS data. And it may be hard to see, but there is quite a deformation along here that does represent. So the first set of calculations I'm going to show are from the Beaufort C. The elastic-decohesive model was incorporated into a material point method, sea ice model. And since not everybody is familiar with MPM, I thought I'd just give a quick overview of what that is. It's a discretization, kind of a particle and cell type discretization where the domain is divided between Lagrangian points and a background grid. We solve the momentum equation on the background grid, but the constitutive model, ice thickness distribution, thermodynamics are all evaluated at material points, as well as and the point about the constitutive model is important because once you have damage, because we're doing Lagrangian, the points are Lagrangian, then we don't have any smearing effect by trying to advect the damage on an Eulerian grid. So this is our computational domain. This is Alaska on the left, the coast of Alaska. And we're simulating 15 days in February and March 2004. This was data we got from Rong Kwok. It's 10-kilometer grid resolution, which is typical for our GPS, but it's actually daily resolution in time, which is higher than the general RGPS data. And so we initialized our simulation with leads calculated in the way I described in the previous slide. And after running for 15 days where we had ocean and atmospheric forcing that were from reanalysis products from the time, we get the following results. So on the far left we have divergence, in the middle is shear, and on the right is vorticity. On the top is the RGPS data, and on the bottom is our MPM results. So one thing I'll note is that one thing we have seen in almost all of our calculations is that we underrepresent divergence compared to RGPS, and so it's not exactly clear why, and it's not just our constitutive model. We've looked at this with the viscous plastic, and they also, it seems like divergence is underrepresented. So that's something interesting. For the shear, qualitatively, they look fairly similar, but we didn't do, and what we should probably do is one of the scale analyses where we look at how everything scales. And then, let's see, and now I'm going to show some, if we look at decohesion opening. So this is basically looking at the crack opening using the method I described for pulling it out of RGPS, and then what we get from our model. We see things look fairly good. There are some discrepancies. We do capture things like this crack along the coast, but up in this area we do have some discrepancies. If we look at distributions of opening magnitude, the distributions are fairly similar, but RGPS definitely has more small scale opening than we see in our model. So we've also looked at global simulations. I'm just going to show the Arctic, but in collaboration with Elizabeth Hunke, we incorporated the elastic-decohesive model into sea ice. So for these simulations, we used the spin-up, an elastic viscoplastic spin-up from sea ice as our initial conditions. And then we also had initial conditions for the crack opening that we put into the elastic-decohesive model. We simulated 2 months in February-March 1997 and 2 months February-March 2004 to do sensitivity analyses, really. We used atmospheric reanalysis and just 20-year average ocean fields for the forcing. This was all run on a 1-degree displaced pole grid, and we wanted to investigate some of the parameters of our constituent model. So in order to see how the different parameters affect the results we get, we looked at a sensitivity analysis where we varied the following parameters: the Young's modulus-Poisson ratio, the strength terms. The shear multiplication factor is just a factor. It really didn't make that much difference. It has something to do with the shear strength. So as you vary the shear strength, that really incorporates what this would be. So, and then an opening, the opening parameter that I had mentioned before. And we looked at responses that include total ice extent, total ice volume, RMS speed, and then some errors, well, a velocity error, and then correlation with divergence vorticity and shear from our GPS. So we did 50 samples. We used Latin hypercube sampling to do this. So among the parameters, we had 2 of the elastic parameters, and then the majority were the strength parameters from the elastic-decohesive model, and this opening parameter, I guess you could call other. If we look at standardized regression coefficients from the sensitivity study, higher the number means the more dependence you have. And there's a lot of variability. Many of the, as I said before, this factor here really didn't have much of an effect on anything, so we neglect it going on. But there are a lot of interesting things in that the tensile strength actually had a strong effect on extent and volume and speed, but the shear strength, not so much. It had a strong impact on speed and more on the vorticity and divergence correlations. So here are some velocity results. On the left is our elastic-decohesive model. On the right is a standard elastoviscoplastic for the same time. And the blue on each are from the model, and the red are from optimally interpolated 2-day motion measurements. And they both actually perform somewhat similarly. One thing we notice of interest is the elastic viscoplastic almost always had much higher drift along the Fram straight than our model did. And here the errors are roughly similar for the 2 models for this example. If we look at deformation, so here divergence, vorticity, and shear over a series of days during which we ran. Top is our GPS, middle is elastoviscoplastic, and then EDC on the bottom. And they are different scales. So our GPS is at 10 kilometer resolution. Our models are at 1 degree, which it's a displaced pole grid. So basically lat long where the pole is moved over Greenland. So you have probably the highest resolution is roughly 25 kilometer in the region we're looking at. So we are a lot more coarse, but we're not really capturing all the features, either in either of the models. As I mentioned before, we're under-predicting divergence. And you get some of the large-scale features if you kind of squint and look at it. But it's not as good as we might hope. Partially, it is a resolution issue. But we were surprised that the EVP looks as good as it does. compared to the EDC on some of these. So for the next set of calculations, we decided to just do an additional sensitivity analysis on just the two strength parameters. And we ran, again, another 50 samples, this time using 2004 data for the forcing. And we looked at a cost function that included the velocity error as well as the correlations between the divergence, vorticity, and shear. And so it's kind of interesting. If we look at the tensile strength for these 50 samples and the error measure, you don't see a big pattern. It's kind of random. But we did find that as you reduce the shear strength, we get a lot better answer. So it's an interesting result. Not entirely clear what the significance is. But a lot of the deformation is in shear, so it probably makes sense that the shear is very important. So for this set of runs, here's another velocity plot for one of our samples. In this case, strangely enough, the EDC did do a lot better in terms of matching the velocities than the EVP. And again, EVP is quite a lot faster in the export. And then both models somewhat underpredict in this region. If we look at deformation comparison from this again, we can see we do get some similar features. Here we have a lot of shear down here, but again, not as good of a match as we would hope. And maybe going to higher resolution will impact that somewhat. That's not entirely clear. So there are clearly areas where the model can be improved. So I'll go ahead and conclude now. The Arctic is changing rapidly, and so we need these high-resolution sea ice models. We want to do predictions, and not so from the scale of days all the way to years and decades for the climate. It's not entirely clear that the same model would be good for going from all those time resolutions, but it's an ideal to get something that would be. Anisotropic rheologies really have the potential to improve forecasts. I mean, we saw in the Beaufort example that we could really capture a lot of the deformation that was going on, but that was at smaller scale. And another point is that we were using actual reanalysis ocean forcing, so that may have had an impact as well. But there's a lot more work to be done. We could improve the crack closure and freezing model. One thing that I think Han is going to talk about a little bit, in this model I mentioned at the beginning that we use an ice thickness distribution where you have some fraction of open water in each cell. And that fraction evolves based on the divergence in the cell, but it's not directly related to crack opening. And so that is somewhat of a limitation. So we know that there's some fraction of open water in a cell, but we don't know what the orientation is, what the orientation of the high thickness ice is. And so tying it directly to the ice thickness distribution would be, I think, a good thing to do. We also need a lot more data comparisons, and in order to replace the model that's been used for 30, 40 years now, I mean, I think there has to be compelling evidence that the complications you're adding are worth it, and that the results are significantly better than the viscous plastic model or the elastic viscous plastic model. And with that, I'll stop.
have a question. Imagine that one crack or one decohesion appear in your model. Okay, so you are opening your crack, and then later on you have some convergent motion. And so in this case, would you have still in your model, I'm not sure, some shear strength along the cracks?
Yeah, so if you have, the way the model works is the strength is only lost in the normal direction to the crack. So if you have deformation in another direction, then you still have strength in that direction. So you still, if you have a shear motion, you can still have strength.
Thank you for your talk. So you seem to compared your deformation products with the RGPS data and the Beaufort Sea. And I thought you did a pretty good job, actually. So you're a bit modest, I thought, about how well it did. You said you underestimated the divergence. But how much of that can be traced down to uncertainty in the atmospheric and oceanic forcing? Because you don't know that very well.
Yes, that's true. But I think the timescales are fairly short, and I think that it's known well enough. It's not the same scale of uncertainty as you would get if we were running an ocean or atmosphere model along with it. I mean, it is reanalysis data that has been kind of optimally obtained from observations, even though they're sparse, right? So there may be, but it is a good question, how much uncertainty comes from the forcing even in that case.
So I'm not familiar with the models, but in this particular case, you've got a linear softening kind of approximation.
Yes.
But it's 500 meters.
Yeah.
So that's 5 million of my cracks.
Right. Which is why it's not really a single crack.
Right. So that's fine. Of course, it means that it's something like 5 million cracks. That's the way,
Right.
But okay, just throwing things in the air. Comparing the previous talk, your approach seems quite different. It's elastic plastic, and you do have this softening regime, softening portion, which is of course associated with fracture energy, kind of explicitly. Any comments on that? Any elucidations?
So it's, I'm not really familiar with the other approach that much, but I'd say our approach really takes a lot from thinking about elastic plastic types of models, and really it tries to create a fracture model or a decohesive model that mimics how an elastic plastic model would work in a lot of cases. And so you have these softening, same type of thing.
In the envelope, it involves the compressive strength.
Yes.
There must have been a fair bit of discussion about that, because...
So I don't know if you know about Schreier very well.
I do know.
Yeah, but he was very insistent on the axial splitting and the compressive strength. Yes.
Because it's not regarded as a material property, of course. So what did you choose? What do you choose to put in there? You go down the envelope, or?
So the parameters we choose kind of dictate how the go back to the so the parameters we choose here really dictate how these normals, oops, let's see here, transition around that. And so where you have your ductile and where you have brittle type fracture. And that can vary depending on what you pick for those parameters.
So I sense that the key difficulty is trying to get an understanding of how everything affects subsequent modeling.
Yes. So, I mean, fundamentally, what we'd like to be able to do is have a predictive sea ice models where we can say with some accuracy, if not what's going to happen in 10 years, but, you know, just for forecasting even, you know, what's going to happen in 3 days, right?
You mentioned that you worked with Elizabeth Huntley to do some global simulations in SICE.
Mm-hmm.
I presume that wasn't using the material point method, or was it?
I'm sorry, what?
Were you using the material point method in that situation?
No. So in that case, it wasn't the material point method. We used the discretization in sea ice, which is, it's mostly an Eulerian finite difference with a little bit of, interesting stuff.
That's what we use as well. So, I mean, was that
Yeah.
any sort of issue with you considering your previous
So
method?
there were some issues with that because in that case we have to advect the damage in some sense, and so that was another issue that might have caused some of the smearing that we saw with the decohesive model. Is when you do any type of advection numerically, you're going to smear things out a little bit. So that's one issue.